Hello, in this lecture we'll answer two questions. In the first question we find out the radius of this circle that blocks quadrangle ABCD, or quadrangle ABCD is inscribed by this circle. So we have to find out the radius of this circle. In the second question we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have quadrangle ABCD that is inscribed by this circle. We know that AC is the diameter of this circle. AB equals to BC. Side AB of quadrangle ABCD equals to side BC. In addition, we know that the perimeter of this quadrangle ABCD is equal to 18 units. That is to say, the sum of its side lengths in total is equals to 18. AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrangle ABCD equals to 16 square units in size. Again, our task is to find out the radius of this circle. So first of all, we'll define the side lengths of quadrangle ABCD with letters. We will define the length of side AB. This side is A. AB equals to BC in its length, therefore BC must be also equal to A. We define the length of side AD as B. And finally, we define the length of side CD of quadrangle ABCD as C. So here we can implement rule 7. Repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So, in the drawing, we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of this circle, therefore peripheral angle ACB must be equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle ABC that subtend on chord AC, that is the diameter of this circle, therefore peripheral angle ABC must be equal to 90 degrees in its size according to rule 7. Likewise, this is peripheral angle ADC that subtend on the same chord called AC, that is the diameter of the circle, and therefore peripheral angle ADC must be equal to 90 degrees in its size according to rule 7. So in the next step, we'll implement the Pythagoras theorem on those two right triangles, on the right triangle ABC, on this right triangle ADC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle ABC, according to the Pythagoras theorem, here by PT is the evaluation for Pythagoras theorem. And right triangle ABC, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. But again, the entire ABC according to the Pythagoras theorem. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is 8, therefore AB squared is A squared plus BC squared. BC is also 8, so BC squared is A squared. So in total, we found out that AC squared equals to A squared plus A squared, that is 2A squared. AC squared equals to 2A squared, according to equation 1. So, in the next step, we'll implement the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, on this right triangle ADC, AC squared, that is the square of the hypotenuse, is equal to AD squared plus DC squared. Again, according to the Pythagoras theorem, in this right triangle ADC, AC squared equals to AD squared plus DC squared. AC is the missing side, so we need to substitute. It is AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus DC squared. DC is C, therefore DC squared is C squared. So in total, if you found out that according to equation 2, AC squared equals to B squared plus C squared. Well, according to equation 1, we only found out that AC squared equals to 2A squared. So in the next step, we recurre the equation 3. It says that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2. AC squared according to equation 2 equals to B squared plus C squared. So in total, according to equation 3, I have found out that 2A squared equals to B squared plus C squared. Here we divide this equation 3 by 2, and finally we get that A squared equals to B squared plus C squared over 2. And again, according to equation 3, A squared equals to B squared plus C squared over 2. It's given us the question that the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and AD is D. AD is B. So in total, AB plus BC plus CD plus DA will be equal to A plus A, that is 2A, plus C plus B. Again, 2A plus C plus B equals to 18. So according to equation 4, we should find out that the perimeter of quadrilateral ABCD equals to 18. According to all these guys in the equation, that is to say 2A plus C plus B equals to 18. It is also given us in the question that the area of this quadrilateral ABCD equals to 16 square units in its size. Quadrilateral ABCD consists of those two shapes. The first shape is this right triangle ABC, the second shape, this is the right triangle ADC. Therefore, it is very clear that the area of quadrilateral ABCD must be equal to the sum of the areas of those two shapes that is consist of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of this second shape, that is the area of this right triangle ADC. So until now, I should find out that the area of quadrilateral ABCD in total must be equal to the sum of the areas of the two shapes that it consists of. That is to say, must be equal to the area of the first shape that it consists of, that is actually the area of the right triangle ABC, plus the area of the second shape that it consists of, actually the area of this right triangle ADC. It is given as the question that the area of quadrilateral ABCD, the area of quadrilateral ABCD equals to 16 square units in its size. Therefore, we'll substitute the area of quadrilateral ABCD by 16. So according to question 5, we found out that 16 equals to the area of the right triangle ABC plus the area of the right triangle ADC. So 16 equals to the area of the right triangle ABC. What is the area of this right triangle ABC? The area of the right triangle ABC must be equal to the base AB times the height BC over 2. AB is A, BC is also A, divided by 2. So it is A times A over 2, that is A squared over 2. And to that, we should know that the area of the first shape, the area of the right triangle ABC, is equal to A squared over 2 square units in its size, plus the area of the second shape, that is the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the height DC over 2. AD is B, DC is C over 2. So it is B times C over 2. BC over 2. The area of the second step, that is of the this equals to b times c over 2 square root in its size. So in total, we found out that 16 equals to a square over 2 plus bc over 2. Here we will multiply this equation 5 by 2, and finally we get that 16 times 2 is 32 equals to a square over 2 times 2 is a square, bc over 2 times 2 is bc. So in total, according to equation 5, we have found out that 32 equals to a square plus bc. While according to equation 3, I have found out that a square equals to b square plus c square over 2. E square equals to b square plus c square over 2. Therefore, we can substitute a square in this equation 5 by b square plus c square over 2 from this equation 3. We do it now and get it according to equation 5. 32 equals to a square, and a square according to equation this equation 3 equals to b square plus c square over 2 plus b times c. So in total, according to equation 5, we have found out that 32 equals to b square plus c square over 2 plus bc. So here we multiply bc by 2 and then divide by 2 in order to come out of this expression, and we get that according to equation 5, 32 equals to b square plus c square over 2. And we have 2 times bc divided by 2. So in total, I have found out that 32 equals to b square plus c square plus 2 times b times c over 2. So here we will multiply this equation 5 by 2. And get it according to equation 5. 32 times 2 is 64 equals to b square plus c square plus 2 times b times c. Here we use the algebraic identity that says that a square plus b square plus 2 times a times b equals to a plus b square. According to this algebraic identity, we get that b square plus c square plus 2 times b times c equals to b plus c square, and it is equal to 64. According to equation 5. In total, according to equation 5, we have found out that 64 equals to b plus c square. So here we'll take a root out of this equation and finally get that the square root of 64 is 8, so 8 equals to the square root of b plus c square is b plus c. So in total, we have found out that b plus c equals to 8 according to equation 5. While according to equation 4, we only found out that 2a plus c plus b equals to 18. According to equation 4, we only found out that 2a plus b plus c equals to 18. So now we can substitute b plus c in this equation 4 by 8 from this equation 5. We'll do it now, we get it from this equation 4. 2a plus b plus c, and b plus c according to equation 5 is 8. It is plus 8 equals to 18. So in total, according to equation 4, we found out that 2a plus 8 equals to 18. Here we subtract 8 from this equation 4, and get it according to equation 4, 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divide this equation 4 by 2. And finally, we get that according to equation 4, a equals to 10 over 2, that is 5. And again, for that, we found out that according to equation 4, a equals to 5 units in its length. So here side AB equals to A and A equals to 5, so AB equals to 5. Likewise, side BC also equals to A and A equals to 5. So BC equals to 5. The next step, we will implement the Pythagoras theorem on this side line by an ABC. Here by PT is the relation for Pythagoras theorem. This side ABC according to the Pythagoras theorem. AC square, this is the square of the hypotenuse, is equal to AB square plus BC square. AC is the missing side, so it is AC, so it is AC square equals to AB square. AB is 5, therefore AB square is 5 square, that is 25. Plus BC square. BC is also 5, so BC square is 5 square, that is 25. So in total, we found out that AC square equals to 25 plus 25, that is 50. So AC square equals to 50. Here we substitute 50 by 2 times 25, so and get that AC square equals to 25 times 2. Here we take the root out of this equation, and we get that AC equals to the square root of 25, that is 5, so inside the root we have to leave 2. So in total, we found out that AC equals to 5 times square root of 2 units in its length. This is side AC. This is the hypotenuse of the triangle ABC, and it is also the hypotenuse of the triangle ADC. But AC is also the diameter of the circle according to what is given as the equation. So the radius that we are looking for, that is the radius of this circle, must be equal to the diameter over 2. That is to say, it must be equal to AC over 2. And we find the radius of this circle is R. The radius R of the circle, that is the radius that we are looking for in this question, will be equal to the diameter AC over 2. AC is 5 times square root of 2. So 5 times square root of 2 over 2 is the length of the radius of this circle. This is the radius that we are looking for in this question. So R equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, R equals to 3.536 units in its length. And this is the answer to the first question. I repeat again, I should find out that the radius R of this circle equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius R equals to 3.536 units in its length. So we finish with the first question. The next step, I will present you the second question and the answer on the second question of this lecture. In this second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is inscribed by this right angle ABC. You know that QS equals to 25, chord QP equals to 24. This is angle ABC, this is right angle. We have here tangent. This is a tangent to the circle at this point. So we define the point of tendency of this tangent. If this circle, this point is point M. So here, tangent SM, that is tangent of this circle is point M. Again, our task is to find out the length of line segment AP that equals to x. We have to find out the value of x. So first of all, we'll implement rule 2 in our drawing. Repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common point to a circle are equal. In the drawing, we have a circle. This is the common point, point P. From this common point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So can I implement rule 2 in our drawing? In our drawing, if we focus on this common point A, from this common point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP equals to x, and therefore AQ must be also equal to x units in its length. In the next step, we'll define the length of this small tangent BM as A. And we'll focus in this connection point B. From this connection point B, we have two tangents to this circle, tangent BQ and tangent BM. And according to rule 2, they are equal to each other. This is to say BM equals to BQ. But BM equals to A, and therefore BQ must be also equal to units in its length. In the next step, we'll focus on this common sum point S. From this common sum point S, we have tangent SM, that is tangent to this circle point M. Likewise, we have here chord PQ of this circle, the extended chord PQ, such as point S. So all the requirements for form 10 are satisfied, and therefore we can implement here on 10. Append quickly on 10, according to on 10. On 10 is for in any circle. In any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true. PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So in the following, we have a circle. This is the common sum point P. On this common sum point P, we have tangent PT. That is tangent to this circle is point T. Likewise, we have chord VA of this circle, the extended chord VA, such as point P. So in this moment, the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So division 4, all the requirements for full 10 are satisfied if you focus on the common sum point S. On the common sum point S, we have tangent SM, that is tangent to the circle point M. In addition, we have here chord PQ, and the extended chord PQ touches point S. Again, all the requirements for full 10 are satisfied, and therefore we can implement here on 10. According to 10, the following equation is true, that SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. As you know, so SM squared equals to SQ times SP. And again, according to rule 10, if you focus on the common sum point P, the following equation is true. That SM squared equals to SQ times SP. SM is the missing tangent, so we limit the city, so it is SM squared equals to SQ squared. SQ is 25 times SP. SP in total equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. Again, SM squared equals to SQ times SP. SM squared equals to SQ, that is 25, times SP, that is 49. Here we take out of this equation. We find again that SM, the missing tangent SM, is equal to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, we actually found out that SM equals to 5 times 7, that is 35. SM equals to 35. Units in its length. So the length of this standard SM is 35 units. As is known. SM equals to 45 units in its length. What is the length of this missing line 7? Line 7 SB. On the one, it is very easy to see that SB in total equals to SM must be M. Again, SM must be M equals to SB. So, I don't know. Let me say 97 SB equals to SM must be M. So SB in total equals to SM, that is 35, plus BM, that is A. So total SB equals to 35 also units in its run. In the next step, we implement the Pythagoras theorem. This plane okay. What is the definition of triangle QBS? Is it a right triangle or not? You know that SM is a tangent to this circle at point M. SM as a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line SM at point B? We have this angle that is a right angle, plus this missing angle, total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So if we found out that the right triangle QBS, the green triangle QBS is a right angle. Therefore, we will implement the Pythagoras theorem on this green right triangle QBS. Here by PT is the abbreviation for Pythagoras theorem. So in this right triangle QBS, according to Pythagoras theorem, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. And again, in the right triangle QBS, according to Pythagoras theorem, QS squared equals to QB squared QS squared equals to QB squared plus BS squared. QS is 25, therefore QS squared is 25 squared, that is 625. And it is equal to QB squared. QB is 8, therefore QB squared is 8 squared. Plus BS squared. BS is 35 times 8, therefore BS squared is 35 times 8 squared. So, okay. In total, we found out that 625 equals to a squared plus 35 times a squared. So 625 equals to a squared 35 outside square. So we'll open the brackets of this expression and we get that 35 outside square equals to 35 outside square equals to 35 squared, that is 1225, plus a square, minus 2 times 35 times 8, that is minus 78. So we have 625 equals to a square plus a square is 2a square, minus 78 plus 1225. So here is subtract 625 from this equation. So in this side of the equation we have reflecting, that is to say 0. While on the other side of the equation we have 2a squared, 178, 1225 plus 625 is 600. So in total we shall know that 0 equals to 2a squared, 178 plus 600. Here we will divide this equation by 2, and we get that 2a squared over 2 is a squared. 178 over 2 is 145a, and 600 over 2 is 300. 0 over 2 is 0. So in total, we should know that a squared was 45a, a squared was 45a plus 300 equals to 0. So here this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 35a plus 300 equals to 0, the variable that we are looking for is a. So x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 35. And finally, the coefficient c equals to 300. So we have all the data that is needed in order to solve this quadratic equation. That is to say, in order to find out the variable that we are looking for, that is a. We just have to put the data that we have of our specific quadratic equation in this formula for x, and in this way we find out the value of the value of the values of a, because x equals to a is the variable that we are looking for. X equals to a. So x equals to a, so we substitute x by a. So a equals to minus b. B is minus 35, therefore minus b is minus 145, that is plus 35, plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. A is 1, c is 300. So minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200. In total, minus 4 times a times c is 1200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we should find out that the variable that we are looking for, A, equals to 35 plus minus square root of 1225 plus 1200 over 2. So A equals to 35 plus minus 1225 plus 1200 is 25, so inside the root we left only with 25 over 2. So A in total equals to 35 plus minus, the square root of 25 is 5 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for A is that A equals to 20 units in its length. A is the length of this distance element QB, and it is also the length of this distance element BN. So according to the first solution for A equals to 20 units in its length. So we have also the second solution for A. The second solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 30, and 30 over 2 is 15. So the second solution for A is that A equals to 15. So A equals to either to 15 or to 20. We have two solutions for A. So in the next step, we will do a construction. We'll find out later why A is a very important thing. The value of A is a very important thing in order to find out the length of line segment X. So in the next step, we will do a construction. But before that, this is the green triangle AQP. The green triangle AQP is an associated triangle because of the fact that side AQ equals to side AP. QP is of course the base of the associated triangle, triangle AQP. So we do a construction, that is to say from point A, we will do perpendicular to the base QP. Again, from point A, we will do perpendicular to the base QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point A in the base QP, this point is point Z. So, in total, we have here the associated triangle AQP, and from point A we go perpendicular AZ to the base QP. Therefore, we can definitely implement here rule 21. So this quicker rule 21. According to rule 21, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have triangle ABC is an isosceles triangle because side AB equals to side AC. From point A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, this angle also equals to 90 degrees according to our construction. And according to this rule, rule 21, the perpendicular AO bisects base BC. Again, the perpendicular AO bisects the base BC from the isosceles triangle, triangle ABC. That is to say, it divides the base BC into two halves. The first half is BO. The second half is OC. Of course, the first half BO must be equal to the second half OC. Each half, of course, equals to BCO2 because side BC bisected. So each half must be equal to BCO2. So BO equals to BCO2, OC also equals to BCO2. So BO equals to OC equals to BCO2. So I can actually implement rule 21 in our drawing. What in our drawing, we have the isosceles triangle AQP. We have perpendicular AZ. According to rule 21, perpendicular AZ bisects the base QP. That is to say, it divides the base QP into two halves. Each half equals to QP over 2. The first half QZ, of course, equals to the second half ZP, and each half equals to QP over 2. So I'll write it down. In the isosceles triangle, again, isosceles triangle AQP, according to rule 21, the perpendicular AZ bisects the base QP. So the first half QZ, of course, equals to the second half ZP. And each half equals to QP over 2. And again, according to rule 21, the perpendicular AZ bisects the base QP. The first half is QZ, and it is of course equals to the second half ZP. Each half equals to QP over 2. Because the base QP has been bisected. So each half must be equal to QP over 2. QP is 24. So therefore QP over 2 is 24 over 2, that is 12. And for this long equation, QP equals to ZP equals to QP over 2 equals to 24 over 2 equals to 12. We have that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. If I found out that QZ equals to 12, and ZP also equals to 12 units in itself, according to rule 21. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angles as alpha, then the size of this vertex angle must be also equal to alpha. So in this green triangle AQZ, this is angle alpha, this is a right angle, therefore this third vicinity must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, this right triangle QBS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first this angle must equal to 90 degrees on alpha according to the sum rule. That's it, that the sum of the angles in any triangle is equal to 180 degrees. It's very easy to see that those two right-hand triangles are similar to each other according to angle similarity rule. That is to say that the right triangle AZQ is similar to this right-hand triangle QBS. Why those two right-hand triangles are similar to each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha and therefore they are equal to each other. So we should find out that all the triangles of this right-hand triangle QBS are correspondingly equal to all the triangles of this right-hand triangle AZQ, and therefore those two right-hand triangles are similar to each other according to angle similarity rule. So, write it down. The right triangle QBS, the right-hand triangle QBS is similar. This is the sign of similar to this right-hand triangle AQZ. According to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of this right triangle SQB or side AQ of this right triangle AQZ is equal to side QB of this right triangle SQB over side QZ of this right triangle AQZ. So SQ over AQ equals to QB over QZ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle QBS or side AQ of the right triangle AQZ is equal to side QB of the right triangle QBS or side ZQ of the right triangle AQZ. SQ is 25 over AQZ, that is the value that we're looking for this question, and it is equals to QB is A over QZ is 12. So in total, we should find out that 25 over x equals to A over 12. Here we will cross multiply this equation and get that 25 times 12 is 300 equals to x times A. So now we very clear why A is so important to us. Because if we know the value of A, then we immediately know the values of x. If A equals to 15, then x equals to 300 over 15, while if A equals to 20, then x will be equal to 300 over 20. That is the reason that assignment A is so important to us. So actually, here we will divide this equation by A and get that x equals to 300 over A. So the value of x is dependent by A. It's dependent in A. For that reason, we have to find out what is the real value of A. A could be equal to either 20 or 15. Okay. So in order to find out what is the real value of A, I draw this right triangle in the circle that is inscribed inside it in a new drawing, and we analyze this right triangle with the circle in order to find out what is the real value of A. Is A equals to 15 or 20? We get the answer to the question by analyzing this right triangle with the circle that is inscribed inside it. So actually, this is the right triangle ABC with the circle that is inscribed inside it and the code from the original drawing. We already found out that QB equals to A, AQ equals to X. We define the point of tendency of the BC with this circle, this point is point M. Likewise, we define the radius of this circle, this point is. We define the center of this circle, this point is point O. We define the radius of this circle as R. In the next step, we join points O and M together by a straight line. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle, equals to R according to our definition. The radius OM is equals to R, the radius OM is drawn to point M, that is the point of tendency of the BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by a straight line. OQ is of course the radius of this circle, is equals to R, and according to equation 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the small quadrilateral Q, O, and B, we have 1, 2, 3 degrees, and therefore this fourth piece must be equal to 90 degrees in its size. So the small quadrilateral Q, O, and B is 4 rectangles. Therefore, we can relate to quadrilateral Q, O, and B is a rectangle. Although that it is in fact a square, we can relate to it as a rectangle. You don't need any more. You don't need to prove that it's a square. It is enough to prove that it is a rectangle. This quadrilateral Q O M B is a rectangle. The quadrilateral Q O M B is a rectangle because it has 4 rectangles. So in this small rectangle QOMB, side OM must be equal to the opposite side QB, but OM is not, therefore the opposite side QB must be also equal to R units in its length. So QB equals to A and QB also equals to R. And R of course equals to A. Okay, in the next step, we will do a construction, that is to say, we will extend the radius MO by a straight line until it touches the circle. We find the touching point of the extended radius MO with this circle, this point Z. MO is a straight line, it is a radius, the point is a straight line. We extend a straight line by a straight line. The result MZ must be also a straight line, of course. So if we focus on the right side of the straight line ZM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of ZM at point O? We have this is the right angle plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. This is to say, from side AB, we go tangent to the circle at point Z again. So, from side AB, we go a tangent to the circle at point Z. It is definitely possible to do it. Because you can choose the right point on AB that will be tangent to the circle at point Z. We define the touching point of the tangent with side AB. This point is point T. Repeat again. TZ is a tangent to the circle at point Z according to our construction. Point O is the center of the circle. Point Z is the point of the circle itself. Therefore, OZ is the radius of the circle. This is equals to R. The radius OZ is equals to R. The radius OZ is known to point Z. That is the point of tendency of tangent Z with this circle. Whenever radius is known to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in total, in the upper quadrilateral TZ on Q, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral TZ on Q, we have 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZ, or Q, side ZO must be equal to the opposite side TQ, but ZO is the radius of the circle that is equals to R, and therefore TQ must be also equal to R units in its length. So we already found out that let's say with QB equals to A equals to R. So from one side, let's say QB equals to A, from the other side, let's say QB equals to R. So again, from one side, let's say QB equals to A, from the other side is equal to R. Or we can say that QB equals to A equals to R, doesn't matter. What about 97AQ? Actually, from one side, 97AQ equals to X, that is the variable that we are looking for in this question, but from the other side, AQ equals to AT plus TQ. Again, AQ in total equals to AT plus TQ. So AQ equals to AT plus TQ. TQ is also in total AQ equals to AT plus R. So from one side, AQ equals to X, but from the other side, AQ also equals to AT plus R. So today we should find out that AT plus R equals to AQ equals to X. AT is the length of line segment. It is a length, so as a length it is a positive number. And therefore AT plus R it is absolutely greater than R because AT is a positive number. So we can write down here that AT plus R it is definitely greater than R. And from this long inequality, we derive that A is smaller than X, or X is greater than A. And we have those two edges, and here we have A is smaller than X, or X is greater than A. So I'm just trying to find out that X is greater than A. And we have two solutions that are possible for A. A could be equal to 20, or A could be equal to 15. We only found out that X equals to 300 over A. So if A equals to 15, then X equals to 300 over 15, that is 20. So if A equals to 15, then X must be equal to 20. Likewise, if A equals to 20, then X must be equal to 300 over 20, that is 15. So if A equals to 20, then X must be equal to 15. So here we have X equals to 15, and 15 is definitely greater than 20. But 20 equals to A, so we can write here that 20 equals to A. And from this inequality, we derive that X is greater than A. Again, 15 is smaller than 20. 15 of course is smaller than 20. 15 is definitely smaller than 20. And from this inequality, we derive that x is smaller than a. Again, from this inequality, we derive that x is smaller than a. Okay. X is smaller than a. This contradicts to our previous findings that x must be greater than a. So due to this contradiction, we cancel the solution. A cannot be equal to 20 and take into account only the second solution of a, that a equals to 15. So, and then x equals to 20. So x equals to 20, it is definitely greater than 15. 20 is greater than 15, and 15 equals to a. And from this inequality, we derive that x is greater than a. X is greater than a, exactly according to what we already found out, that x must be greater than a. It is not contradicts our previous findings, and therefore the correct answer to the question is that a equals to 15, and then x equals to 20 units in itself. 97AP is equals to x, is equal to 20 units in itself. And again, I should found out that this is line segment AP is equals to x, and x equals to 20 units in itself. So we finished to answer on the second question. The next step, I will summarize the lecture. I will start with the first question, of course. Actually, we will repeat on the solution of the first question and then on the solution of the second question. The first question, our task is to find out the radius of this circle that blocks quadrilateral ABCD, or quadrilateral ABCD is described by this circle. So we have to find out the radius of this circle. It's given us a question that AC, called AC, is the diameter of this circle. In addition, we know that AB equals to BC. Side AB of quadrilateral ABCD equals to side BC. We also know that the perimeter of this quadrilateral ABCD equals to 18 units in itself. That is to say, the sum of its side lengths, AB plus BC plus CD plus DA, in total equals to 18. We also know that the area of this quadrilateral ABCD equals to 16 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we defined the side lengths of quadrilateral ABCD with letters. We define the length of side AB as A. Because of the fact that AB equals to BC in itself, therefore BC must be also equal to A. We define side AD as B and side CD as C. In the next step, we implemented rule 7 in our drawing. So repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is triangle ACB that subtends on chord AB, that is the diameter of this circle, and therefore according to this rule 7, triangle ACB must be equal to 90 degrees in its size. So according to this rule 7, any triangle that subtends on the diameter of the circle must be equal to 90 degrees in its size. This is triangle ABC that subtends on AC, that is the diameter of the circle, therefore it must be equal to 90 degrees in its size according to rule 7. Likewise, this is triangle ADC that subtends on the same diameter of diameter AC, and therefore it must be equal to 90 degrees in its size. So in the next step, we calculate the Pythagoras theorem on those two right triangles, the right triangle ABC and the right triangle ADC. According to the Pythagoras theorem, in a right triangle, the square of the products equals to the sum of the squares of the perpendicular. So in that right triangle ABC, it means that AC square, that is the square of the products, equals to AB square plus BC square. And again, the right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus BC square. So AC square equals to AB square. AB is A, therefore AB square is A square, plus BC square. BC is also A, so BC square is A square. So total, AC square equals to A square plus A square, that is 2A square. AC square equals to 2A square, according to equation 1. In the next step, we implemented the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, in this right triangle ADC, AC square, that is the square of the products, equals to AD square plus DC square. AC square, that is the square of the products, equals to AD square plus DC square. AD is B, therefore AD square is B square plus CB square. Plus CD square. CD is C, therefore CD square is C square. So in total, AC square equals to B square plus C square. Again, AC square equals to B square plus C square, according to equation 2. While according to equation 1, we already found out that AC square equals to 2A square. So we have two different equations for AC square. Therefore, we created equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. AC square according to equation 1 equals to 2A square, while AC square according to equation 2 equals to B square plus C square. So in total, we found out that according to equation 3, 2A square equals to B square plus C square. Here we divided this equation 3 by 2, and we found out that A square equals to B square plus C square over 2. We know that the perimeter of this quadrangle ABCD is equal to 18. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and DA is A. DB is B. DA is B. So in total, AB plus BC is A plus A, that is 2A, plus CD, that is C, plus DA, that is B. So in total, the perimeter of this quadrangle ABC, it is 18, it equals to A plus A, that is 2A, plus C plus B. Again, 2A plus C plus B equals to 18. According to equation 4, we should found out that 2A plus C plus B equals to 18. We know that the area of this quadrangle ABCD is equal to 16 square meters in size. Quadrangle ABCD consists of those two right triangles, and therefore the area of quadrangle ABCD must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of this second shape, that is the area of this right triangle ADC. So the area of quadrangle ABCD must be equal to the sum of the areas of the two shapes that it consists of. The first shape is triangle ABC, and therefore it is the area of the first shape, that is the area of triangle ABC, plus the area of the second shape that it consists of, that is the area of the right triangle ADC. It's given us the equation that the area of quadrilateral ABCD equals to 16, so we substitute the area of quadrilateral ABCD by 16, and it is equals to the area of triangle ABC plus the area of triangle ABC. So what is the area of this right triangle ABC? The area of the right triangle ABC equals to the base AB times the area to the base BC over 2. AB is A, BC is A over 2. So it is A times A over 2, that is A squared over 2. So if we found out that the area of this right triangle ABC is equal to A squared over 2. Is equal to, so 16 equals to A squared over 2, plus the area of the other right triangle ADC. The area of this right triangle ADC is equals to the base CD times the area to the base DA over 2. CD is C, DA is B over 2, so it is C times B over 2. The area of the right triangle ADC equals to BC over 2 square roots in size. So if you found out that according to equation 5, 16 equals to A square over 2 plus BC over 2. Here we multiply this equation 5 by 2, and we found out that 16 times 2 is 32 equals to A squared plus B squared. We only found out that according to equation 3, A squared equals to B squared plus A squared over 2, so we can substitute A squared in this equation 5 by B squared plus A squared over 2 for this equation 3. We did it, and we found out that according to equation 5, 32 equals to A squared, that is B squared plus A squared over 2, plus BC. Here we multiplied BC by 2, and then we divided by 2 in order to become a factor of this expression. And we found out that 32 equals to B squared plus C squared over 2, and we have 2 times BC over 2. So total 32 equals to B squared plus C squared plus 2 times BC over 2. So we multiply this equation 5 by 2, and we found out that 32 times 2 is 64, equals to B squared plus C squared plus 2 times B times BC. And 64 equals to B squared plus C squared plus 2 times B times C. Here we used the algebraic identity that said that A squared plus B squared plus 2 times A times B equals to A plus B squared. According to this algebraic identity, we get that B squared plus C squared plus 2 times B times C equals to B plus C squared. So 64 equals to B plus C squared. Here we took out of the equation and found out that the square root of 64 is 8, and the square root of BC squared is B plus C. So we found out that according to equation 5, B plus C equals to 8. This is according to equation 5, while according to equation 4, we already found out that 2 times 2A plus B plus C equals to 18. So we can substitute B plus C in this equation 4 by 8 from this equation 5. We did it, and we found out that 2A plus BC plus B plus C. B plus C is 8 equals to 18. So 2A plus 8 equals to 18. Here we subtract from this equation 4 8, and we found out that 2A equals to 18 minus 8 is 10. So 2A equals to 10. Here we divided this equation 4 by 2, and finally found out that A equals to 10 over 2, that is 5 units. A equals to 5 units in its length. And again, I should found out that A equals to 5 units in its length. So BC, that is A is 5, AB is also A is 5. The next step, we implemented the Pythagoras theorem in this right triangle ABC. According to the Pythagoras theorem, in this right triangle ABC, AC squared equals to AB squared plus BC squared. Right? In the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC is the missing side, so it is AB is 5, therefore B squared is 5 squared, that is 25. Plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, actually, found out that AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 25 times 2, so AC square equals to 25 times 2. We took hold of this equation and found out that AC equals to the square root of 25, that is 5, so inside out we left only with 2. So AC in total equals to 5 times square root of 2 minutes in its length. AC is the product of those two materials, but AC is also the diameter of the circle. If the diameter of the circle is AC, it means that the radius must be equal to AC over 2. So the radius that we are looking for in our question, it is equal to the diameter AC over 2. The diameter AC is 5 times square root of 2, so 5 times square root of 2 over 2 is the radius of the circle, or the length of the radius of the circle. So in total, we found out that the radius that we are looking for this question, that the radius of this circle equals to either 5 times square root of 2 over 2 units in the circle. From there some numbers, the radius of this circle R equals to 3.536 units in its length. So finish to repeat on the first question, in the next step repeat on the solution of the second question. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is described by the right angle ABC. Know that QS equals to 25, chord QP equals to 24. This is angle ABC, this is the right angle. This is tangent SM. This is tangent to the circle, point M. So again, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So first of all, we implemented rule 2 in our drawing. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing, we have a circle. This is the common standpoint, point P. From the common standpoint, point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of tangent PB, or P equals to PB. So we can actually implement rule 2 in our drawing. We have put in our drawing. We have the common standpoint, point A. From this common standpoint, point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in its length. In the next step, we define the length of tangent B. We define the length of this tangent BM as A. And focus on this common standpoint, point B. From this common standpoint, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to A units in its length. In the next step, we focus on this common standpoint, point S. From this common standpoint, point S, we have tangent SM, that is tangent to this circle, is point M. Likewise, we have chord PQ, the extended chord PQ, that is point S. So all the chords of rule 10 are satisfied, and therefore we can implement rule 10. So repeat quickly rule 10, according to rule 10 is true in any circle. In any circle, if AB is the chord in the circle, and PT is the tangent to the circle, then the following equation is true, that PT square equals to PA times PB, and PT square equals to PA times PB. So in the drawing, we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents. We have tangent PT, that is tangent to the circle, point T, and we have this is called BA. The extended called BA touches point P. So in this line, the following equation is true. That PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So what I mentioned before, you can implement all 10 in our line. All other points of all 10 are satisfied if you focus on this common example point S. From this common example point S, you have tangent SM that is extended to this against point M. Likewise, the extended chord PQ touches point S. Again, all the requirements of all 10 are satisfied and the whole can implement all 10. According to all 10, the following equation is true. That SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. And again, if you follow the common point S, according to all 10, the following equation is true. That SM squared equals to SQ times SP. SM is the missing tangent, so it is SQ is 25, SP in total is equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. And again, if you found out that SM squared equals to SQ times SP. SM is the missing side, so it is SQ is 25, SP is 49. So SM squared equals to 25 times 49. Here we took out all of this equation and we found out that SM equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. This is saying that SM is equals to 35 units in its length. What is the length of this line segment? SB. SB equals to SM plus BM. And SB equals to SM plus BM. So SB in total equals to SM, that is 35, plus BM, that is 8. So in total, SB equals to 35 from the units in its length. SM is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line SM at point B? We have this angle that is right angle, plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Therefore, the triangle SQB is a right angle. So in the next step, we implemented the Pythagoras theorem on this green right angle SQB. The green right angle SQB, according to the Pythagoras theorem, QS squared equals to QB squared plus BC squared. Again, QS squared equals to QB squared plus BS squared. QS squared equals to QB squared plus SB squared. QS is 25, therefore QS squared is 25 squared, that is 625. Plus QB squared, QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 from 6, therefore SB squared is 35 from 6 squared. So in total, if you found out that 625 equals to 8 squared plus 35 from 6 squared. So 625 equals to 8 squared. We have 35 from 6 squared. We will open the brackets of this expression and find out that 35 from 6 squared equals to 35 squared. That is 1225 plus 8 squared plus 2 times 35 times 8, that is 178. So 625 equals to 8 squared plus 8 squared is 2 squared, 178 plus 1225. Here we subtract 625 from this equation, so in this side of the equation we have nothing. This is to say 0. While on the other side of the equation we have 2 squared, 178 plus 600. Here we divided this equation by 2 and found out that 0 over 2 is 0, 2 squared over 2 is 8 squared, 178 over 2 is 145, and 600 over 2 is 300. So in total, we should know that a squared minus 35a plus 300 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. and we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0, the variable that we're looking for is of course a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 45, and the coefficient c equals to 300. So we have all the data in order to solve out this quadratic equation, and that is to say, in order to find out the value of the values of a. You just have to put this data inside this general equation for x, and this way we find out the value of the values of a, because a is the variable that we are looking for in this question. So we did it, and we should find out that x is equals to a. So we substitute x by a, and it is equals to minus b. B is minus 35, therefore minus b is minus 45, that is 35, plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. A is 1, c is 300, so in total minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200. So in total minus 4 times a times c is minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we have found out that a equals to 35 plus minus. Side root we have 1225 plus 1200, that is 25 over 2. The square root of 25 is 5, so in total we have found out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20 units in its length. Well, the second solution for a is that a equals to 35 times 5 over 2. 35 times 5 is 30, and 30 over 2 is 15. So the second solution for a is 15. The second solution for a is 20. So in the next step, we implemented rule 21. Actually, we did the construction and then implemented rule 21 in our problem. This is the rectangle AQP. In the rectangle AQP, side AQ equals to side AP, and therefore the rectangle AQP is an isosceles triangle. QP is of course the base of the isosceles triangle, triangle AQP. So we did a construction, that is to say from point A we go perpendicular AZ to the base QP. Again, from point A we go perpendicular AZ to the base QP. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to rule 21, the perpendicular AZ to the base QP bisects the base QP. That is to say, divide the base QP into two halves. The first half QZ must be also equal to the second half ZP. Each half must be equal to QP over 2, because QP is bisected. Each half must be equal to QP over 2. So QZ equals to ZP equals to QP over 2. This again in the associated triangle AQP according to rule 21. The first half of QP, QZ must be equal to the second half ZP, QP, and each half must be equal to QP over 2. QP is 24, 24 over 2 is 12. So for this equation, we draw that QZ equals to ZP equals to 12. This is QZ is 12, ZP is also 12. Those two angles are defined as vertex angles, and vertex angles are equal to each other. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So in the right triangle AQZ, this is angle alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in an triangle. Likewise, this small green right triangle SQB, this is angle alpha, this angle equals to 1 this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees also, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Those two right angles are similar to each other according to angle similarity rule. That is to say, the right angle AQZ is similar to this right angle SQB according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees plus alpha, and therefore they are equal to each other. So if you found out that all the figures of this right angle SQB are corresponding equal to all the angles of this right angle this right angle AQZ, and therefore those two right angles are similar to each other according to angle similarity rule. If you found out that the right right triangle QSV similar, this is the sign of similar to the right triangle AQZ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SQ of this right triangle SQB or side AQ of this right triangle AQZ is equal to side QB of this right triangle SQB or side QZ of this right triangle AQZ. Side SQ of the right triangle QBS or side AQ of the right triangle AQZ equals to side QB of the right triangle QBS or side QZ of the right triangle AQZ. SQ is 25, AQ is X, QB is A, and QZ is 12. So in total, 25 over X equals to A over 12. Here, of course, multiply this equation and find out that 12 times 25 is 300 equals to AX. Here we divided this equation by A and find out that X equals to 300 over A. But now we know that X equals to 300 over A. If A equals to 20, then X equals to 300 over 20, that is 15. But if A equals to 15, then X equals to 300 over 15, that is 20. So we have to verify what is the real value of A, whether it is 15 or 20. In order to verify what is the real value for A, I copy this right triangle ABC with a circle that is inscribed inside it, and analyze the new drawing in order to find out what is the real value of A. Is it 15 or 20? So actually, this is the right triangle ABC with a circle that is inscribed inside it. We already found out that QB equals to A and AQ equals to X. And here we find the point of tendency of the BC with the circle the same. We define the radius of the circle as R. We find the center of the circle, this point is point O. Then we join points O and M together by side line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equals to R. The radius of M that is equals to R, the radius of M is drawn to point M, that is the point of tendency of the BC with this circle. And whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to 1. Point Q is the point of tendency of tangent AB with this circle. We join points O and Q together by side line. OQ is the radius of the circle that is equals to R. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to 1. So in quadrilateral Q, O, and B, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in size according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral Q, O, and B, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QOMZ, QOMB, side OM equals to the opposite side QB. But OM is R, therefore the opposite side QB must be also equal to R units in its length. In the next step, we did a construction, that is to say, we extended the radius MO by side line until it touches the circle. This point, we define the touching point of the extended radius MO with this circle. This point is point Z. So, when you extend the straight line by straight line, the result MZ must be also straight line. So MZ is the straight line. If you focus on the right side of the straight line, MZ point at point O, Here the sum degrees must be equal to 100 degrees according to all three. So we can have the right side of MZ at point O, we have this angle that is right angle, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. In the next step we did another construction, that is to say from side AB, we do a tangent to the circle at point Z. But again, we do the tangent in such a way that it will be tangent to the circle at point Z. We define the touching point of the tangent with side AB, this point is point T. So again, I repeat again that TZ is a tangent to the circle at point Z according to our construction. So in the component O1, this angle equals to 90 degrees. Why? Because the radius OZ, point O is the center of the circle, point Z is the point of the circle Z, therefore OZ is the radius of the circle, this is equals to R. This is equal to R. The radius OZ, this is equals to R, the radius OZ is 1 to point Z, this is the point of tendency of tangent OZ with this circle. And whenever, this is the point of tendency of tangent TZ with this circle. And whenever your radius is 1 to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in the upper quadrangle TZOQ we have 1, 2, 3 degrees, and therefore this fourth missing angle must be equal to 90 degrees inside. Therefore quadrangle TZOQ is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZOQ, side ZO must be equal to the opposite side TQ, but ZO is R, therefore the opposite side TQ must be also equal to R units in its length. We already found out that BQ equals to A and BQ also equals to R. Again, BQ equals to A and BQ also equals to R. AQ equals to X, AQ equals to X, but AQ also equals to AT plus CQ. AQ equals to AT plus CQ. TQ is R, so in total AQ equals to AT plus R. So from one side AQ equals to X, but from the other side AQ also equals to AT plus R. AT is a positive number because it is a length. And therefore, plus element, it is definitely a positive number. Therefore, AT plus R is definitely greater than R because AT is a positive number. Again, AT plus R is greater than R. And from this inequality, we derive that A is smaller than X. Again, A is smaller than X, or X is greater than A. So if I know that X is greater than A, I know that X is greater than A, and we have two solutions that are possible for A. The first solution for A is that A equals to 20, and the second solution for A is that A equals to 15. We only found out that X equals to 300 over A. X equals to 300 over A. So if A equals to 15, then X equals to 300 over 15, that is 20. So X equals to 20. So if A equals to 15, then X equals to 20. Likewise, if A equals to 20, then X equals to 300 over 20, that is 15. So if A equals to 20, X equals to 15. And if A equals to 15, then X equals to 20. So here we have X equals to 15. But 15 is definitely less than 20. And 20 equals to A. Yeah, 20 equals to A. 20 equals to A. And from this inequality, we will derive that X is less than A. X is less than A. But we already found out that X is greater than A. So we have a contradiction here, and due to this contradiction, we cancel the solution. A can never be equal to 20. Therefore, we choose the second solution for A, that A equals to 15. Now, we will not have any contradiction anymore. Why? Because X that is equal to 20 is definitely greater than A. The X that is equal to 20 is definitely greater than 15. 20 is greater than 15, that equals to A. 20 is greater than 15. 20 is greater than 15, that equals to A. From this inequality, we have that x is greater than a, exactly like we already found out that x is indeed greater than a. So the solution to the question is that x equals to 20. 978p is equals to x is equal to 20 units in its length. Okay, again, we should found out that 9 segment AP this is 9 segment AP is equals to x is equal to 20 units in its length. Okay, thank you very much.